My name is Gerald Cecil. This is a report on our ongoing study of the Milky Way's nuclear jet. We're studying the fossil record of the Milky Way's most recent Seyfert phase. There are two scales that this appears on. In the 1 to 60 kiloparsec scale, we have the effects of the central source ionizing the surroundings, in particular an arc of the Magellanic Stream. This was studied by Bland, Hawthorne et al. In a couple of papers, indicates an outburst from an AGN spectrum of between 2.5 and 4.5 megayears ago. This process probably inflated the two large bubbles we see here, the Fermi bubbles inside, and then the recently discovered or confirmed E Rosita bubbles outside them. The other scale is at light minutes to light days, detected by the Gravity Consortium looking at orbits, and the accretion disk measured by ALMA recently, and then constraints on a possible jet from VLBA visibilities. Must be launched within 35 degrees of the line of sight, otherwise the visibilities are extended more than they appear. The other scale that's important is, and the one that we're focusing on now, is 100 parsec scales and down to a fraction of a parsec. At the 100 parsec scale, the evidence for outflows was first found in Sofui's radio observations of the galactic center lobe, then dust lobes detected in the MSX data published by Bland, Hawthorne, and Cohen in 2003. And those are relevant because they indicate a very massive flow, unlike the radio continuum measurements, which would be very small in mass and therefore relatively low in energetics. With the dust, the energetics came up to 10 to the 56 ergs, which is sufficient to reject a starburst as the inflator of these structures. So here are the radio observations now of Haywood 2019 with Meerkat, updating the Sofui results. And you can see that they extend and overlap very nicely with the dust lanes. There they are again. And then these are X-ray observations published by Ponti in 2018 showing hot channels. And you combine the two, you can see the radio and X-ray overlap quite nicely and produce these bubbly structures that we'll talk about later when we talk about our simulation results. At the 0.1 parsec scale, Lee et al. In 2013 came up with a candidate X-ray jet. So all of these things are important in a larger sense because the Milky Way begins to look like an active galactic nucleus. Here are contours of NGC 1068's radio structure superimposed on the Milky Way, and you can see there's lots of interesting similarities between the two in terms of scale and bubbly structure and so on. So the only thing missing from the Milky Way at this point is this concentrated active jet structure that we see in 1068, which is not apparently present in the Milky Way. And that's the focus of our study, is there evidence for this on a smaller scale. So we wanted to assess the linkage between a jet, the VLBA, and a 200 parsec scales using archival data shown here, and also 3D simulations with these characteristics. 10 to the 41 erg per second jet focused onto fractal ISM clouds, and so far our ongoing studies varying the jet launch angle onto an ISM organized into the circumnuclear disk around the ionized mini-spiral. The mini-spiral provides us with orbits that we can use to pin down the geometry and quantify the required energetics. Over to the right we have the Meerkat data, and we've now zoomed in to the JVLA data to show the mini-spiral at the center and then the circumnuclear disk around it. And this is a notional jet axis that we're putting in here that's consistent with the VLBA data and also some other parameters we'll see in a moment. Looking now at Passion Alpha, there's nothing obvious connecting the nucleus, but if we move up here you can see an interesting interaction site that we'll talk about a little bit. Here are the X-ray observations from Chandra, and this was what Lee et al. Discussed as the jet structure to the south, this very concentrated feature. If we now zoom in on that and look at the mini-spiral in ionized gas, we can see, as they saw, a possible interaction site here where the jet has emerged, strikes this particular arm of the mini-spiral, mass loads up to the point where there's sufficient material in it to produce the X-ray synchrotron emission shown here. And the X-ray data and X-ray models are all shown in Lee et al. And are quite convincingly jet-like. So what we did was to take the mini-spiral orbits from Zhao, including the uncertainties, which are shown here now. And you can see there's quite a large range in uncertainties for the structure of these orbits. And if we then place the interaction site, we can say perpendicular to our line of sight, which is shown here. We can identify the interaction zone, and we can see that a range of jet inclinations could still intersect this collection of possible orbits. That's now shown down here. Here are the different jet inclinations. Here's the interaction site. These are the orbits that remain for those particular orientations. The interaction site provides us with a range of jet orientations shown here, most of which are redshifted on this side of the nucleus, which would be up over here. So trying to identify structures that are on that side of the nucleus, we found in the ALMA data this channel at 77 kilometers per second, and you can see that it is not falling exactly along the jet axis, but this linear feature is definitely focused towards the center. So we believe that what we are seeing is a parallax effect produced by the jet interacting with the surroundings closest to it on the circumnuclear disk. So shown here, you can see the interaction site, you can see the jet orientations from our viewpoint, from the side viewpoint. There's a top view, and you can see that this region over here is closest to the jet, and therefore we experience the strongest interaction, and that's what we believe we're seeing in that site there. So what does this interaction look like? In the channel maps from ALMA, we have the velocity structure produced in the CS line and many other lines. Here is CS, and you can see that as the velocities increase, we move from a central strand to a double strand. So at maximum redshifted velocities, we see a double-sided structure, and we see a single-sided structure in the bluest velocities, all still redshifted by the tilt of the jet away from us. So here is an interesting structure that does this, cylindrical flow, an expansion from this axis produced by the hot cocoon. The red-shifted side of it is attenuated going into the surroundings. The blue-shifted side is a central line down the structure, and that's what we see. And then the intermediate velocities or lowest velocities that we see are on either side of this strand, which is what we see on the side. So we think this is a reasonable interpretation of the flow field. What are the properties of this flow? Well, Suboy et al.'s data from ALMA come in a variety of different spectral lines, and the bright lines indicate that this is a weakly shocked gas, less than 10 to the 4 particles per cubic centimeter, and they derive a mass of 1,000 T over 200 Kelvin solar masses. So this is a very massive molecular flow if the temperatures are down around 200 and potentially higher because of the shocking that occurs. To the north region beyond that, so beyond this region down here, farther out, we ask, are there any other interactions possible? And we focus on this interaction site up here in the Passion Alpha image, and we can see trails of radio continuum and X-ray gas moving up in that direction. That structure looks like this in Passion Alpha and like this in JVLA 5.5 gigahertz. Very similar appearance, and focused along the boundary here is a very interesting sharp arcuate structure that we're going to obtain near-infrared spectra of very soon to see if we can see evidence for shocked emission. Where is this located? Depending upon if the jet angle is launched on any of the axes associated with a southern interaction, then it could be as close as 10 parsecs. If they're on the VLBA scale, where we miss the southern interaction, but are now consistent with the VLBA scale launch angles, then it could be anywhere from 20 parsecs on. And this is one of the things we will try to establish with our infrared data cubes. So now let's take a look at the simulations, which are ongoing, still in progress. We're looking at the density output of jets emerging from the circumnuclear disk. We view this structure from the left-hand side, and the two distributions here are showing you different distributions of gas within the circumnuclear disk. And you can see that the entrainment that results from the jet is fairly different in both of these situations in detail, illustrating the complexity of doing a comparison between a fractal gas distribution like this and observations. So for example, we have clouds being lifted off here and quite complex clouds being lifted over here. What's interesting, though, is that gas has been lifted off on both the front and the back sides of the circumnuclear disk. And the flow of this gas is redshifted in both cases, and so that matches the observations. Whether we see it on the front side or the back side is really something we're trying to pin down, but both sides will make the observed quantities. Now what we're doing is moving to plus minus 500 parsec scale, representing to the larger scale for Meerkat and E Rosita. The left-hand side shows us a volume rendering in temperature. The right-hand side shows us the equatorial plane slice now in gas density. We can see that the hot gas emerges very quickly out of the polar regions in less than 500,000 years. And the equatorial region is very quickly filled with the hot gas as well. It drives and erodes the interstellar clouds away. Of course, they're being lifted out of the plane, which we can't see in this particular slice on the right-hand side, but you can see them being lifted out to higher elevations on the left-hand side. So these simulations run for several million years, and you can see that the outcome is to completely clear out the central region of the galaxy. Now, a future eruption, if it occurred, would be operating in this sort of an environment with some relaxation, so you would expect to see a different outcome. This represents the first outburst. We're clearing the material out for the first time. Now we can look at radio, and on the left-hand side we see the radio surface brightness. On the right-hand side we have a volume rendering of that emission at a later time, and the orange on the right-hand side is showing you the interstellar clouds with the radio emission structured. You can see that the radio emission emerges as blobby structures, arcuate structures, depending upon whether the jet has hit individual interstellar clouds in the central region and driven them out to larger scales. So it's a very stochastic process. The jet is organized down on smaller scales, but quickly breaks into these bubbly structures exactly as observed. You can see an outburst just occurred there as stuff flowed out from a particularly strong collision. And the Fermi bubbles are in the top quarters and bottom quarters of this diagram, showing you these things do emerge out of a realistic galactic potential and flare out into the observed structures. Now we can look at the X-ray emission. So there's a volume rendering of the X-ray emission by itself, and you can see it very rapidly fills up the entire volume as we saw before, and then starts to launch into space, into high latitudes very effectively. Does not show the complete bubbly structure we see in the radio, which is interesting. I'll show a comparison of the two wavelengths. We ran the outflow with the correct orientation, which is shown here, superimposed. And you can see the jet follows quite nicely along the structure we see. And we have now projections of the data sets, jet tracing, and this is the velocity field. You can see that they agree quite well. So our conclusions, summary, are that we have studied and confirmed a jet ISM interaction in the Milky Way within 5 parsecs projected from the center. We confirmed the Lee et al. Results of a mini-spiral interaction on the south side, that small X-ray jet structure, but we now find new aligned gas features on the north side in the ALMA data sets. And these structures on the 5 parsec scale linked quite nicely to the 500 parsec scale. Our simulations now in progress on both scales attempt to match the velocities, energetics, and constrain the time dependence and the repetition of these outbursts. I think the most important result we're getting from the simulations thus far is to show that we can find redshifted entrainment on the front and back sides of the circumnuclear disk. The fact that the circumnuclear disk is tilted provides us with a very effective entrainment. So we're studying the details of that, and we will report in more detail later.